Hey, everybody. All right. Um, so as we start to zoom out and go from talking about stars to talking about galaxies, there's a logical transition point here, and that is how do we measure the distances out to stars and then galaxies? Um, and this diagram here gives you a sense of each of those blue stripes is a different method, in a sense. Um, because not every method for finding distance works for everything. Um, we've been talking so far this semester about measuring the distances to stars using parallax. And why have we spent so much time using parallax? Well, it works great, right? It's easy. All you got to do is measure that parallax angle and you've got the distance. And until a few years ago, that worked great for getting us out to like 1,000 or 2,000 light years. Um, and it tended to sort of max out around there. Given the new parallax measurements using the Gaia satellite, we can measure distances out to about 10,000 parsecs, which is fantastic. But even that fails at some point. Even this parallax method um, stops working because at some point stars get so far away that the parallax angle becomes smaller than the resolution limit of your telescope. And then the stars look like they don't move with parallax at all. And if you can't measure the parallax angle, you can't get the distance. At which point you got to do something else. So that's why there are a whole bunch of tools in our toolkit for measuring distance, because no one method to measure distance works out to super cosmic distances. And so what do you do after that? What do you do after parallax has stopped working anymore? Well, you got to come up with some other way. Um, One way to do that is with the technical term is spectroscopic parallax. I think they use that term in the homework. Um, but another simpler term for it is main sequence fitting, where you take an HR diagram, right? Luminosity versus temperature. Well, this isn't exactly a luminosity um, versus temperature diagram because the vertical axis here isn't luminosity; it's absolute magnitude, which are just two ways of saying the same thing, right? So this is essentially another version of an HR diagram where the red line here is the main sequence. If you're measuring these main sequence stars in absolute magnitude versus temperature. And so if you take a group of stars in some other neighborhood of the galaxy, and this really works best when that group of stars are really close together in space, like say for instance in a star cluster. If you have a star cluster, all of those stars are close together in the sky because they are all close together in space. And since all of these stars are close together in space, they're all the same distance from Earth. And so if you take the stars in a star cluster and you measure their apparent magnitudes and their temperature, then you plot these stars in this cluster. Each of these dots here is a star in the cluster with their apparent magnitude and their temperature. And most of the stars are going to lie along this line because you look at that and go, oh, well, okay, that's the main sequence. The stars going up off this way, well, that must be the red giant branch. But we really care about the main sequence here. Because remember, every main sequence star is governed by its mass. Right? Every main sequence star with the same mass is going to have the same luminosity, the same absolute magnitude, the same temperature. Which means the only reason why this main sequence is down below this main sequence is because this line is absolute magnitude, this line is apparent magnitude. Why is there a difference between absolute and apparent magnitude? The only reason why these stars look fainter is because they must be farther away. So by measuring this, by plotting this magnitude versus temperature diagram for these stars in the star cluster, you can look at this and go, well, these stars are so many magnitudes fainter, therefore it must be this many parsecs away. So that's great, because using this is a fairly simple and straightforward way to do it. You can say, all right, I now know the distance to this cluster. And if you know the distance to that star cluster, that means you know the distance to every star in the cluster, and now you know the distance to a few hundred or a few thousand stars all at the same time. Boom, done. So that's super handy. It really works best, and it really only works very well for star clusters, which luckily there's lots of star clusters out there in the galaxy. But if you're not looking at a cluster, if you're not looking at stars in a cluster, how do you do main sequence fitting? You really can't. So you got to come up with some other method. Another way to measure the distances to stars is if you can find some standard variable stars. There are, just to give you the broad idea, just to give you the big idea, there are a handful of variable stars that you can figure out the absolute magnitude for without having to know the distance first. First off, what is a variable star? A variable star is a star whose brightness changes with time. That's it. It's nothing more complicated than that. A variable star is just any star that has an apparent magnitude that changes in time. So eclipsing binaries are variable stars, because when those two binary stars eclipse each other, their brightness changes. But here we're talking about something very different and very specific. The most powerful of these standard variable stars are what are called Cepheid variables. And a Cepheid variable varies in brightness because the star is physically pulsating. The star is physically expanding and contracting. I've got a bit of a cartoon here, right? A Cepheid variable is not a main sequence star. It's not a stable star. These Cepheid variables are unstable. There isn't an equilibrium between pressure and gravity. When you take that Cepheid variable and when pressure is stronger than gravity, the star expands and then it cools off. And when the star cools off, then pressure drops, the gravity pulls the star back inward, and the star collapses down again and heats up until the pressure builds up and the pressure causes the star to expand again. So these Cepheid variables do not have a steady hydrostatic equilibrium. They hover around, these stars hover around stability, but they're unstable. Pressure and gravity are constantly fighting each other, and this star expands, contracts, expands, contracts. It cools off, heats up, cools off, heats up, and therefore the luminosity is changing. When the star heats up, it gets brighter. When the star cools down, it gets dimmer. So that you can watch this star over the course of several days and watch it get brighter, dimmer, brighter, dimmer, brighter, dimmer, brighter, dimmer. And so if you watch that star, and if you see a star that gets bright and then cools, dims down, and gets bright enough, bright again, then dims down, brighter enough, dims down, and if that does that over the course of several days, that's the telltale sign that you're looking at a Cepheid variable. Henrietta Leavitt was one of those women working at the Harvard Observatory in the early 20th century, and she accomplished a lot of things. But one of the things that she did by herself, one of the big discoveries that she did on her own, sort of in her spare time, is that she found a whole bunch of Cepheid variables, and she noticed that they don't all oscillate, they don't all pulsate with the same period. So what is the period? When I say the period, what I mean is the time that the star takes to get bright, cool off, and then get bright again. It turns out that the longer the period of the star, the brighter it is, the higher luminosity it is. So there are a bunch of Cepheid variables close enough that we can get parallax distances, and if you can get the parallax distance, you can figure out the luminosity. And so if you take a bunch of Cepheid variables whose luminosities you know, and you plot, when you plot the luminosity versus the period of pulsation, then it turns out that they all lie along this pretty straight line right here. And this becomes a huge benefit. Because if you know that all Cepheid variables lie along this line in period and luminosity, this graph is what's called the period luminosity relationship for Cepheids. And so if you say, okay, well, now what if I discover a brand new Cepheid? How far away is it? I don't know. I just discovered it. It's this faint Cepheid, and I see it pulsating, and you say, well, how much time does it take? How much time does it take for that star to pulsate once? And you say, well, if that star has a period of 30 days, if that Cepheid has a period of 30 days, every Cepheid variable with a period of 30 days has a luminosity of 10,000 solar luminosities. Boom. You now know what the luminosity of that star is. And if you know the luminosity, you know the absolute magnitude. And if you know the apparent magnitude, which is easy, right? The apparent magnitude is the thing you're measuring directly. If you know the apparent magnitude, and if you know the absolute magnitude of the star, what else can you figure out? You can figure out distance. So you don't have to. Because all Cepheids lie along this line and you've figured out this line, all you got to do is measure the period of pulsation and you've got the luminosity, you've got the distance. So Cepheid variables are one of these rare objects in the universe where you can figure out the luminosity without having to know the distance first. And since you know the luminosity, you can compare that to the apparent magnitude, or compare the absolute magnitude to the apparent magnitude is even easier. And then you can find the distance. Finding Cepheid variables and determining the distance to things using Cepheid variables was the main job that the Hubble Space Telescope was built for. Right? This is not the only thing the Hubble has done, obviously. The Hubble Space Telescope has been a discovery factory for 30 years. But when they were designing the Hubble telescope, they designed it with one main mission in mind, and that is look for Cepheid variables. Not only in our galaxy, but also because you've got the kind of resolution, because you can see the sky much more clearly when you're out in space, because you don't have the atmosphere. Right? When you don't have the atmosphere muddying up your image, you can take pictures of nearby galaxies much more clearly. And so you can take a picture like this. This is a picture of this galaxy. So here's the whole galaxy. This galaxy is called NGC 300. And using the superior sight of the Hubble, you can find individual stars in this galaxy. And some of these stars are going to be Cepheids. Cepheids are rare, but they're not so rare that they're hard to find. They're kind of easy to find because they pulsate, they're blinking, right? These stars are flickering, whereas most stars have a constant apparent magnitude. So if you watch a galaxy like this steadily, if you watch this galaxy steadily for a few days, some small but large enough number of these stars in the galaxy are going to be pulsating, they're going to be noticeable. And if you, all you've got to do is find the Cepheid. All you got to do is find the Cepheid, measure its period, and if you got the period, you can figure out the luminosity, you can get the distance to that star. And here's where it's really awesome. Because if you can figure out the distance to this star, you've got the distance to the entire galaxy. Why do we want to measure the distances to these galaxies? Because the reason why they spent the time and the energy to build the Hubble Space Telescope to do this doesn't sound like the most amazing thing, right? Take a picture of a galaxy, find some Cepheid variables. Is that worth building an entire space telescope about? It is, for this very important reason. How big is the universe? How old is the universe? These are not easy questions. But if you know how far away the galaxies are, if you can figure out the distance to galaxies, then you can start figuring out, well, if I know the distance to this galaxy and that galaxy and this galaxy, then you can start making a measurement of, well, how big is the whole universe? And if you can start measuring the size of the whole universe, then you can start asking questions like, well, when did it all start? When did the galaxies all start moving away from each other? How long ago was the Big Bang? When did the whole universe, capital T, capital U, when did the universe come into existence? That's what the Hubble Space Telescope was built to do. These basic fundamental questions of how big, how old, when did this all start? And by this all, I mean literally everything. You can start getting some very good answers to those questions. All you got to do is find a bunch of Cepheid variables in these galaxies, and you've got your answer. And that's what the Hubble Space Telescope's main mission was when they launched it in 1990. And then once they got that project done, it was like, hey, great, pop the champagne, huge success. Now let's run the telescope for 20 more years and see what else it can figure out, which it is a lot. So the Cepheid distances, measuring distances out in the universe using Cepheids works great, out to about 75 million light years. Once a galaxy gets beyond 75 million light years, if a galaxy gets really far away, what's it going to look like? It's going to look small. And so let's say you can't zoom in on this galaxy. What if this galaxy is so far away that this is the best picture of it you can get? And then you say, well, find the Cepheid stars in that galaxy. And you go, I can't pick out the individual stars. The whole galaxy just looks like one big diffuse swirl. If you can't pick out the individual Cepheids, you can't get the distance using Cepheids, so this method has failed again. So this works great, right? This method works great for galaxies out to 75 million light years. And then we need to find a better way. Then we need to switch gears to another method to get distances beyond that. At which point we start finding some really useful properties of galaxies based on what those galaxies do to light. So one thing that we haven't talked much about in this semester is the Doppler effect. So let's go over that for just a second. No, wait, what am I saying? You already saw the Doppler effect with the binary stars homework. Okay, so I don't need to start from scratch then. Okay, but just like with stars, if a galaxy is moving away from us, then its light is going to be redshifted, and when a galaxy is moving toward us, its spectrum is going to be blue shifted. So what is a galaxy made of? Well, a galaxy is made of stars and also gas, right? Stars and the interstellar medium. And what is the interstellar medium made of? It's made of cold gas. So a galaxy gives you an absorption spectrum because the stars that it's made of give you an absorption spectrum, and then you get extra absorption from the interstellar medium. So you can use this same trick for galaxies as you do for stars. Take those absorption lines from the galaxy, and if those absorption lines are red-shifted, the star must be moving away from you. If the galaxy is blue-shifted, it must be moving toward you, and how fast the galaxy is moving determines the degree of the redshift or the blue shift. And this, when you're talking about galaxies, is huge because you can figure out how galaxies are moving very quickly by using the Doppler effect. Galaxies are millions of light years away. And yet, if that galaxy is moving toward us or away from us, you can tell from the Doppler effect immediately. The Doppler effect only depends on the radial velocity, not the distance. So, how does this help us get distance? How can we use the Doppler effect to give us distance? Well, in a few ways. The 70s were kind of a weird time, because studying galaxies in the 70s meant there were lots of good ideas. People had been figuring out how general relativity worked and stellar evolution, and the problem was that with the 70s and telescopes weren't that good. Telescopes and cameras weren't as good yet. So in the 70s, you had all these great theories of physics to explain what galaxies and stars should be like, but the ability to actually take images and get reliable data was not up to speed yet. The revolution in CCD cameras and big space telescopes and big ground-based telescopes hadn't caught up yet. And so in the 70s, you had a bunch of people trying to figure out, how do we measure the distances to galaxies? Because we certainly can't find little Cepheid stars in a galaxy millions and millions of light years away. So one of the ways that people came up with that, to say, most of these methods that were determined in the 70s, people don't really use anymore because they are really complicated and kind of flaky. Why would you do that when you could just find a Cepheid variable? Which we can do using current technology out to a certain distance. One of the methods that people still find pretty reliable, one of the methods that still works pretty well, is what's called the Tully-Fisher relation. And the Tully-Fisher relation is basically a relationship between how fast a spiral galaxy is spinning and its luminosity. And so here's take this with a grain of salt. This only works for spiral galaxies because a spiral galaxy is a disk of stars spinning in one direction, either clockwise or counterclockwise. So this only works for spiral galaxies, but okay, better than nothing. And so what you do is you measure the Doppler shift. The stars on this side of the galaxy, if they're spinning toward us, then this starlight is blue shifted. The stars on the other side, if those stars are spinning away from us, then that starlight is red shifted. So by measuring the red shift on one side and the blue shift on the other, you can figure out how fast that whole galaxy is spinning, what the speed of the stars are, and it turns out when you calibrate this, that the rotational speed of the galaxy and the luminosity of the galaxy are a pretty tight little straight line relationship. The faster a galaxy is spinning, now let's think about why. Right? Why would that be? Why would there be a relationship between the rotational spin and the luminosity? And the answer, what's the one thing you would want to know about a galaxy? Mass, of course, right? If a galaxy is more massive, then that galaxy is pulling on the stars with a stronger gravity. And if the galaxy is pulling on the stars with a stronger gravity, they're going to spin faster. The stars are going to be orbiting around the center of the galaxy faster. And if the galaxy has more mass, then there are going to be more stars. And if there's more stars, the star will be a higher luminosity. So basically what you're looking at is just a measure of mass. The lower the mass means the galaxy spins slower and it's dimmer. The higher the mass of the galaxy, the stars are going to orbit faster and the galaxy will be brighter. This is something you can measure, right? Use that Doppler method to say, look at the stars orbiting away from us, look at the stars orbiting toward us. And if you say, well, okay, if this spiral galaxy is spinning this fast, then it must be this luminosity. And if you know the luminosity of the galaxy, you can do the math to say what the absolute magnitude of the galaxy would be. And if you have the absolute magnitude of the galaxy and you compare it to the apparent magnitude, you've got the distance. So it's not that hard. It takes a little bit of work. You got to measure the blue shift over here and the red shift over there, and that's a little bit of work. But it's pretty good. It works pretty well, right? It is considerably better calibrated, and it is considerably more reliable than some of the other ways that people were trying to um, do in the 70s. And so, we still use it today. Um, so if you have a spiral galaxy, and again, that's a limitation. This only works for spiral galaxies. But if you want to get the distance to a spiral galaxy, you can use this relationship. Not so bad. This will get you out to about 600 million light years. So you can measure the distance to a spiral out to, like 600 million light years, at which point this fails. Why? Because if you look at a spiral galaxy 600 million light years away, the galaxy just looks like a little smudge, and you can't quite see that it's a spiral galaxy anymore. It just looks like you may be able to tell it's a spiral, although not really. 600 million light years away, that galaxy just looks like a little smudge of light in your image, in which case it's very hard to point your telescope and go, oh yeah, this is the left side and that's the right side. No, it's all just a little smear of light. So you can't really get the rotational speed, and then you can't get the distance using this method. So what do? You gotta switch to another method. These days, the gold standard for measuring the distances to galaxies is with white dwarf supernova. A white dwarf supernova is a supernova, right? It is a star that is exploding catastrophically. And when a star goes supernova, it basically gives off the same amount of light as its entire host galaxy while the star is exploding. That one explosion is the brightness of a galaxy. So you can see these things halfway across the universe. You can see a supernova billions of light years away. One of the supreme ironies of supernova is that type 1 and type 2 supernovas all have the same luminosity. They all have about the same luminosity. The difference is type 1 supernovas, which is, remember, a type 1 supernova is when a white dwarf blows up. A type 2 supernova is when a high mass star blows up. I said all supernovas have about the same luminosity. Well, type 2 supernovas could be a little brighter or a little dimmer. It's a supernova. It's always going to be bright. But not all type 2 supernovas have the same luminosity because, hey, the higher the mass of the star, the brighter it's going to be when it blows up. But a white dwarf supernova always has the same mass. Because remember how you get a type 1 supernova. You get a type 1 supernova when you take a white dwarf and you push that white dwarf right up to the limit of its mass. Right? The maximum mass that a white dwarf can have is 1.4 solar masses. And so if you take a white dwarf and it accretes some more mass, usually from a close binary companion, when that white dwarf gets too close to the maximum mass limit, the star explodes and it unleashes 1.4 solar masses worth of energy. Always the same amount of energy, because every white dwarf supernova comes from the same amount of mass. And so a white dwarf supernova is absolutely a standard candle. What is a standard candle? We've been talking about this for a few minutes now. A standard candle is the type of object where every example of that object, every example of that type, has the same luminosity and the same absolute magnitude. So it is a standard brightness because they're all the same luminosity. Cepheid variable, right? You could say every spiral galaxy that has the same rotational speed has the same luminosity. So that's a standard candle. Every Cepheid that has the same pulsational period has the same luminosity. So those are a standard candle. Although different Cepheids have different luminosities if they have different periods. But they are standardizable, right? If you know the period, you know the luminosity, it's standardized. There's no variability here. Every white dwarf supernova has an absolute magnitude of negative 19.3. Doesn't matter whether the white dwarf supernova is close to us or far away. If you see a white dwarf supernova, if you see a supernova explode, and these things, you tend to notice them because there you are, you're looking at a galaxy one day, and then all of a sudden there's a giant flare up, and then that flare up takes, a few weeks or a few months to fade away. That's a supernova. If you find a white dwarf supernova, you know right off the bat, hey, every white dwarf supernova has the same absolute magnitude. Then all you got to do is compare that absolute magnitude to the apparent magnitude that you see, and you've got the distance. You've got the distance to the supernova, and therefore you have the distance to that entire host galaxy. And that means that you have the distance to every star in that host galaxy, even if that galaxy is billions of light years away. If you can find the white dwarf supernova, you can get the distance to that entire galaxy out to billions of light years. That's what makes this the gold standard. You can get the distance using those white dwarf supernova. You can get the distances to any galaxy. If you can find the white dwarf supernova, you can get the distance to that galaxy out to 5 to 8 billion light years, which is about half the distance, half the size of the universe, basically. So this diagram here that we saw at the beginning, one of the names for this diagram is what's called the cosmic distance ladder. Because it's like a ladder, right? When you're climbing a ladder, you go up one rung at a time. Well, that's what we do for this method, right? We have all of these different methods for measuring distance. And if you can use parallax, great, use parallax. But once parallax fails, you got to switch to something else, like main sequence fitting. And main sequence fitting can get you out pretty far until it fails, and you got to switch to something like Cepheids. And once that fails, you got to switch to something like the really distant standard candles like white dwarf supernova, which can get you out to distant galaxies. This is how we've got really good answers these days to how old is the universe? How big is the universe? When did the Big Bang happen? When did all of this come into existence? How long has this been going on? For the last 10 or 15 years, we've got really good answers because we've got really good measurements for the distances out to cosmically faraway galaxies, mostly using white dwarf supernova. So when you say, or when somebody says, oh, and I'm sure I've said this many times over the semester, when you say, oh, the universe is 13.8 billion years old. Oh, the Big Bang happened 13.8 billion years old. The obvious thing to say is, how do you know that? It's not like anybody was around 13.8 billion years ago to write it down, right? How do we know that that's how old the universe is? How do we know these things? We know it because you can see these really bright standard candles halfway across the universe to tell us how big the universe is and how long ago this all started. There's one last piece. There's one rung to this ladder that isn't on this diagram. And that is the expansion of the universe. Because if we can measure the expansion of the universe, if we can measure how fast the universe is getting bigger, then we can start saying, well, if the universe is expanding this fast, when did the expansion begin? And that tells us when the Big Bang happened. That tells us how old the universe is. But you measure just like every rung in this ladder, every rung in the ladder is calibrated, is determined from the knowledge that we have before, right? Because we measured the parallax of nearby stars, we have the standard main sequence to compare the main sequence of a cluster to. Because there are Cepheid variables that we have parallax distances for, we can figure out the period luminosity relation. Because we've got the distances to galaxies using Cepheids, we can calibrate, and we know out to these big distances what the absolute magnitude of every white dwarf supernova is. The last rung here is to say, let's take these distances using white dwarfs and figure out how far away the galaxies are and when they all started moving away from each other. When did the Big Bang happen? So that, we're not going to get there just yet. We're actually going to end the semester talking about the beginning of the universe, which I guess has a nice symmetry to it. Before we can get there, though, we've got to talk about galaxies. We've been talking about, okay, how do you measure the distances to galaxies? Okay, cool. But what else can we figure out about galaxies? What do they look like? What are they made of? Why are galaxies the way that they are? We got to make some heads or tails of that before we can really get to the big not philosophical, but the big questions of where did we come from? Where are we going? When did this all start? How old is everything? The big questions. We got to deal with what we can figure out before we can go the next logical step and say, all right, so now that we've got a handle on stars, let's get a handle on galaxies. Okay, now that we've got a handle on galaxies, let's get a handle on the whole universe. So that's what we're going to be doing for the rest of the semester, is zooming out to say, let's take what we know about the smaller nearby stuff, and then build on that to zoom out and say, okay, what about the bigger thing? And then zoom out some more, and what about a thing bigger than that? And zoom out some more and say, what about the biggest thing? What about the whole universe? So that's where we're going to end the semester. So, hopefully this has given you some good overview on these cosmic distance determination methods. That should, so you should be able to finish up the homework and finish up the tool belt activities, get those done, and then we'll start talking about the structure and history of our Milky Way galaxy and then all the other galaxies. All right, so get that done. I'll see you next week. See you on the other side. Bye.